Production funding for QED with Dr. B is provided by American Electric Power Foundation, Boundless Energy for Brighter Futures, and by viewers like you. Thank you.
I'm Dr. Frederick Bertley, immunologist and educator. Science is everywhere and for everyone, and it's all around us, shaping our lives every single day. In this series, we'll look at cutting-edge research, talk to the scientists who are charting new frontiers and solving today's problems to make all our lives better. When a scientist or mathematician demonstrates a proof of concept in their work, they often use the term QED, Quod Erat Demonstratum. That roughly translates to quite easily demonstrated. Welcome to QED with Dr. B. We hear a lot these days about climate change, how important it is, and how the data tells us that our climate is changing. But what are the scientists talking about? What is the data? How do we find it and analyze it? And how does it tell us that the climate is really changing? We're going to talk about all that, and to kick us off, we're going to do a little experiment. Now, I've done a lot of hands-on demonstrations over the years, and this is one of my favorites. In this bowl is a lump of dry ice. Dry ice is a solid form of carbon dioxide, or CO2. You probably remember from your high school science class that at room temperature, dry ice turns directly into a gas, and this is called sublimation. When we place warm water in the bowl, then we accelerate this sublimation process. Now put a little liquid soap around the rim of the bowl, and then take a string and run it over the top, and we have a bubble of carbon dioxide gas. This carbon dioxide bubble we created with dry ice occurs naturally all over the planet. But it's not carbon dioxide from dry ice that gets trapped in the bubble. It's carbon dioxide from the atmosphere, along with other gases like nitrogen and even some organic material. Scientists can analyze these trapped bubbles and extract data that describes the atmosphere from recent times to hundreds of thousands of years ago. Now, where can we find these time capsule air bubbles? Our first guests are the world's experts in this very field. Dr. Ellen Mosley Thompson and Dr. Lonnie Thompson are both geologists and founders of the Ice Core Paleoclimate Research Group at The Ohio State University. And they have been traveling the globe to hunt for these time capsules trapped deep inside massive pieces of ice. So you both have done so much research on climate change to better help us understand it. Tell us about your research and tell us about your trips.
We're ice core paleoclimatologists, which means that we use the ice cores that we've collected around the world to tell us about what Earth's past climate has been. And we do this by measuring the various chemical species and the dust and the pollen and everything that falls out on a glacier eventually becomes buried, just like a multi-layer cake, and the oldest layer is at the bottom and the youngest layer is at the top, and we come along with our drills and we drill through that and we get a history or a record. Most of my work is in the polar regions, Antarctica and Greenland, and Lonnie has been working for the last, as I have, for the last 40 years, but he works in the low latitudes on the glaciers that are on top of some of the world's highest mountains.
Yeah, I think I've had the pleasure of working in 16 different countries, drilling ice cores, getting to know the people, setting up the logistics. And by doing this around the world and having these records also from Greenland and Antarctica, we can start to put together a global picture of how climate has changed. And we're particularly interested in things like how's the temperature change? I mean, our instrumental records only go back 150 years. We know climate varies on much longer time scales. And what the ice does is provide us a perspective of those changes. And there are very few archives that actually allow you to determine how much precipitation fell in the past. But by measuring the thickness of these layers, we can determine the year-to-year variability in precipitation in these diverse parts of the world. So they're fantastic records.
Let's drill down a little bit, no pun intended. Explain what actually is an ice core, how do you drill them, and what exactly are you looking for in the ice cores?
Well, the ice core is a cylinder of ice. The size of the cylinder depends on the drill, and we design our drills here. They have to be lightweight portable systems to take them up to 20,000 feet on a mountain range. So every piece has to be portable. And in the ice cores, we cut them about 3 feet in length. They go into a special bag, and they're labeled so we know where they fit in the sequence. They go into a special tube, and then they go into insulated boxes, and they have to be kept below freezing for the whole transit out of these remote parts of the world. Okay. And we now have over 4.5 miles of ice in our freezers downstairs, and they come from parts of the world where the glaciers that I drilled earlier in my career are now gone. So they're one in only ice cores.
All right, so you have miles and miles of these ice cores. They're each roughly 3 feet long. What are you actually looking for in these ice cores?
In the Greenland ice cores, because Greenland is downwind of North America, we can actually look at the Greenland ice cores and tell, for example, when the United States implemented the Clean Air Act in 1970, we can monitor all those pollutants from the Industrial Revolution. Up, Clean Air Act 1970, sulfate starts coming down.
Really?
We can look at nitrate and see nitrate is flat until about 1950. What was that? That was the Green Revolution, when post-World War II, think of the baby boomers, and population on the planet was just shooting up. And the fear was, how will we feed all these people? Oh, well, we're going to grow more food. Well, how do you do that? You have to use more fertilizer, nitrogen and phosphorus. That's what you use. We measure that on the Greenland ice sheet. But you can go back and actually look at like smelting different metals. And in Peru, that's particularly been interesting.
Tracing back to the Incas and when they were smelting, you can actually correlate that history?
Yes.
Through an ice core. And talk about what happened.
Well, and these are interesting questions, because we know when metallurgy started in Europe and those parts of the world, but we don't in South America. And yet in the ice, there's a history of the heavy metals that come from smelting.
Sure.
And so you can document that.
So talk to us about that, because you made the nice correlation between measuring these different ions and these particles and these molecules to give you kind of a historical representation of what happened in people. Make the link to climate change. What are you looking at in there that's telling you, wait a minute, our climate is actually changing?
We measure the oxygen and hydrogen isotopes. That's one of the key measurements that we make. The temperature in the atmosphere when the water vapor condenses and the snowflake forms, and then the snowflake falls out on the glacier and it's buried. That carries with it the temperature record. The other thing that the ice cores provide is the history of the composition of our atmosphere. That's the beauty of the ice cores, is that these bubbles get trapped in the ice and they contain ancient atmosphere. Carbon dioxide is one of the major greenhouse gases that we're concerned about. If you keep increasing the concentration of that in the Earth's atmosphere, the Earth loses its capacity to cool itself. So we know what the important greenhouse gases are, but if you look at the history of those greenhouse gases as provided from the ice cores, you'll see these glacial interglacial cycles of about 100,000 years, and then you come up to the last 150 years, and then you look at those gases go up, and where we are now, you can project that back 800,000 years, almost 1 million years, and never has the CO2 risen above around 300 parts per million, and we're at 415 now. And we know what these gases do to the climate. So that's proof positive that it's human activity that's driving much, not all, but much of the changes that we're seeing with the warming of our planet.
With that, is it reversible? What can we do in terms of our daily behavior, monthly behavior, yearly behavior as individuals and as countries to help reverse that if it is reversible?
It's a multifaceted solution. We have to slow our emissions. We have to come up with technologies that help us take those gases out of the atmosphere. We can't wait for the biosphere and for nature, essentially, to absorb all those and utilize those. We need so many people working on this problem from so many different disciplines and perspectives. We need our engineers. We need all those young people out there to help us. And I say us, I mean the scientific and engineering communities, to solve this problem.
Humans have had impacts on our environment as long as we've been here. It's just that today we have 7.8 billion of us, and we're having a huge impact. So the human activity on the planet is recorded in these annual archives that are on these mountaintops and in these polar ice fields. The problems that we face are international problems. They can only be solved by working together. How do we learn to adapt to the change that is coming? And we can only do that by communicating and working together.
Well, I have to say, you guys may specialize in ice cores, but you have a warm heart, and I guarantee you are an inspiration for the next set of scientists that you
Well,
said
we're
we
going to need them.
The ice cores the Thomson study have provided a history of greenhouse gases over hundreds of thousands of years. The data shows that the amount of carbon dioxide in the atmosphere is higher now than it's been in the past 800,000 years, due in large part to human activity. Like a heat-trapping blanket, the more greenhouse gases in the atmosphere, the more heat is trapped inside. It's a global issue, and it will take all of us to understand and discuss this data and then make informed decisions for the future. Our next guest has a very unique perspective on this. Former astronaut and Guinness Book of World Records holder, Dr. Kathy Sullivan, was the first American woman to walk in space, and in 2020, she and her colleague were the first to reach the deepest known point in the ocean. It's not often that I have the pleasure of speaking to someone who's gone up in space and seen that perspective of planet Earth, and then of course dove down deep into the ocean. And of course, on top of that, you were the head of NOAA. So I really want to ask a very simple question, a question about something that's very important to all of us on the planet, climate change. How is climate change impacting the oceans? We don't hear that talk too much.
The ocean is far too left out of most conversations about climate. And there are a couple of reasons that I would cite. One is in terms of really understanding climate change and developing the scientific capability to make better forecasts of what's coming at us when. You can't do that unless you have a lot of data from the ocean. The climate system is the interaction of the sun, the atmosphere, and the ocean. That's what produces climate.
Oceans absorb a lot of solar energy from the sun, and ocean currents carry this heat all around the globe. Remember, oceans cover over 70% of the Earth's surface. As the currents carry this heat around the globe, they are regulating climate. Just as the heart sustains the body by controlling the circulation of blood, the oceans are sort of like the climate's heart, sustaining it by controlling the circulation of things like heat and humidity.
If you're talking today and tomorrow, you're talking weather. If you're talking longer than 2 weeks or a month, you're talking climate. It's the longer term patterns of that stuff. And it's the sun, the atmosphere, and the ocean. But on the planet, it's mainly the ocean that drives that. So we've got to be sure we're taking the right amount of data on the ocean and about the ocean if we're going to have the kind of forecast, predictive capability that can help us get ready. So the ocean is actually physically expanding a bit. That's a fairly small effect. It's helping to absorb about half of the excess carbon dioxide that goes into the atmosphere, because the ocean is a big carbon pump. So it's been helping us, it's been protecting us in a sense from the excess CO2. It's going to run out of the room to do that. It will absorb so much CO2 at some point it can't absorb anymore. Here's the thing that is most commonly forgotten and most, I think, worrisome to me and should be to all of us. You put more CO2 in the ocean, you make the water slightly more acidic. How does the food chain of the ocean work? And it goes from little organisms up to bigger and bigger organisms, right? The bulk of the little organisms make small shells out of calcium carbonate, like seashells, but miniature. And that stuff will dissolve if the water gets too acidic. So making the ocean more acidic by shoving more carbon dioxide into it risks making it a weak acid soup that we might not notice when we go swimming at the seashore. But the critters that are, they're the grass in the meadow that everything else in the ocean feeds off of. They might die out because they can't make their shells.
So you're in the space shuttle, you have that view that just a few people have of our dear planet Earth. With that perspective in particular, what would you say about what the public really needs to understand about climate change, and why should we care about climate change? From, again, the perspective of the astronaut looking down at our beautiful blue planet.
What you should understand is that you need to be thinking like an astronaut, and you need to be looking after and maintaining your life support system. And that is the ocean and the atmosphere. Every other breath you take, that oxygen came from the ocean, from the living organisms in the ocean. There is no form of life anywhere on this planet that is disconnected from the ocean. And there's really nowhere anywhere on this planet that's disconnected from everywhere else. If you pick up like that little critter that you saw swimming up through the camera in our video, if you manage to catch that guy and bring him up to the surface and study him scientifically, odds are you would find microplastics in his gut. Marianas Trench is hundreds of miles from any little speck of land, and it's the deepest place in the ocean. If there's anywhere you might think couldn't possibly show any sign of the hand of man, couldn't possibly have any connection to you sitting here in Columbus, Ohio, it does.
Listen, you heard it here first from 1 out of 7.7 billion people on the planet, literally the only person who can claim expertise from space to the bottom of the depths. Climate change is important, and every little thing we do matters on that. Thank you so much, Dr. Sullivan. Now, let's turn to modeling. Scientists can use computers and the laws of physics to predict the future. Dr. Kate Marvel is a climate scientist and storyteller. She's an associate research scientist at NASA Goddard Institute for Space Studies and Columbia's Engineering Department of Applied Physics and Mathematics. Well, Dr. Marvel, thank you so much for joining us on QED. We're so excited to have you on board.
Oh, thank you so much for having me.
You're very welcome. We'll jump right into it. So tell us, what does climate modeling actually mean?
The way I think about it is our planet is made up of stuff, air and water and rocks and ice, and all that stuff has to obey the laws of physics. We can write down equations that describe how everything is going to behave. But because there's a lot of stuff, it gets really, really, really complicated. And a lot of times we can't solve those by hand. We need to use a computer to solve those equations. So the kind of climate models that I work with are a lot of equations. If you printed out the climate model that I work with, you'd have probably 10 to 20,000 pages of code. So we're talking a lot of complexity here. But really, it just boils down to stuff that obeys the laws of physics. We can write down equations and we can solve those equations, and those equations tell us what stuff is going to do in the future.
Why is climate modeling so useful? What does it actually tell you when you crank that 20,000 pages of code?
Right. So a lot of people will tell you there is no planet B, and that's true. But that also applies to doing science with the planet. We don't have a control group. We can't ask everybody to go move to Mars for 200 years while we see what the Earth does without us. So climate models are really useful because we have a planet, a toy planet on the computer, and we can see how it responds when we set off a volcano or trigger an ice age or put a lot of carbon dioxide in the atmosphere. And so climate models allow us to do experiments in a way that we wouldn't be able to do on the real planet.
Can you compare and contrast climate modeling with what weather predictions are about? So what, meteorologists might do?
A weather model works by tracking air masses and bits of moisture and following those around in the atmosphere. Now, that stuff gets really chaotic really, really quickly. It's easy to know where an air mass is going to move in the next 10 seconds. But the next day, there's a lot of uncertainty that comes in. And 10 days out, your predictability really goes out the window. So it's really, really, really difficult to understand weather predictions 10 days out. Marshall Shepard, who is an unbelievable climate scientist at the University of Georgia, I'm going to steal this from him. He says, weather is your mood, but climate is your personality. So we think about climate as sort of the average weather over a really, really long period of time. And because we're considering really averages and not day-to-day variability, the sources of predictability, the things that make climate change understandable, are different than the things that make weather predictable. So a climate model works on the same equations as a weather model, but it takes more things into account. It takes the deep ocean into account. It takes ice melting into account. It takes the reaction of the land surface into account. And so they're similar, but a climate model and a weather model are fundamentally different things.
What specifically are you doing using climate modeling? What question do you want to answer?
So one of the things that I'm really interested in is a really basic question, which is how hot is it going to get? And I say that to people and people say, well, what on earth? Like, you had one job, climate scientists. Why don't you know that? Above all, we don't know how hot it's going to get because we don't know what human beings are going to do. We don't know whether we're going to cut carbon dioxide and other greenhouse gas emissions, or if it's just going to be business as usual all the way through the next century. But even if you took out that uncertainty associated with what humans are going to do, there's still uncertainty about how the planet reacts because we've never done this experiment before. We've never changed atmospheric chemistry so quickly. And so as a result, there's a lot we don't understand about how the planet itself reacts to that sort of big kick to the system, that big shock. And so that's something that I'm really interested in looking at. What don't we understand and how do we narrow that down?
In science, we talk about, or in general, we talk about that aha moment. Can you think about an aha moment, either as a kiddo or as an adult scientist? Can you share an aha moment in your life?
I mean, one of the awkward things about being a climate scientist is that you have these aha moments. You look at the satellite observations or you look at surface-based data sets and you realize that what has been predicted is actually coming true. But as a climate scientist, those things that are coming true are not happening on a climate model. They're not happening on your computer. They're happening in the real world. And they're happening on this amazing planet that we live on. So I have these aha moments often, but then they're also mixed with, oh my gosh, like what is happening to this planet? What are we doing to it? I did my PhD in astrophysics. So I used to study the entire universe. And what I realized when I was doing that is that this is really the only place in the entire universe that's any good. Earth is the only good planet. And there's so much amazing stuff that happens on this planet. And we are so unbelievably lucky to live here. And so that's something that I really wish people would understand.
In this episode, we looked at some of the important data scientists are using to understand our climate. From the atmosphere hundreds of thousands of years ago, captured in ice cores, to the smallest creatures in the oceans, scientific data informs how we talk about climate and understand how it's changing. We've learned how modeling using very powerful computers can leverage massive amounts of data to give us a better perspective now and for the future. Now that's quite easily demonstrated. QED with Dr. B. Find us on Facebook, Twitter, and Instagram, and I'll see you next time.
Production funding for QED with Dr. B is provided by American Electric Power Foundation, Boundless Energy for Brighter Futures, and by viewers like you. Thank you.